this new concept is going to be something that you just got to accept as a fact of life, okay? And it's one of the concepts that up until today, I cannot really explain using my own words as well. And that's simply because there is no name for this concept, which is a little bit weird, right? But ever since this concept was introduced or found out in the past, people started using this without even giving it a name, right? So you can imagine how abstract this is. So for this concept over here, my recommendation to you as a student who just want to take your A-levels, right, is to just take it as it is, right? There's a lot of things in this whole syllabus that we can go in depth and really try to understand the crux of it. But this is one of the concepts that I would recommend you just take it as it is, right? Because if you really want to go and deep dive into this, by all means, please feel free to do so. But just for the sake of everyone else over here, I will just give you this concept over here. Okay, so previously, we learned that expectation of a discrete random variable, right, is also known as the average, or rather the expected average outcome in the long run, right? That's the whole idea behind it. So now, what happens if instead of just taking x, right, and then putting it into ex over here, what happens if we have a discrete random variable, we pass it through a function first, so gx, and then we try to find the expected value of the output of the function, right? So now the question is, what happens if we apply a function to the random variable first before trying to find the expected value in the long run? So for this concept over here, applying the function over here has no change to the formula, which means that it's still the summation of the output, right, of the function multiplied by the probability of px equals to x, right? So it's exactly the same as previously. So if you look over here, previously we have x multiplied by px equals to x. So you can see that they are exactly the same, okay? And this concept over here is one of the things that people try to explain in the past, but they found it very hard. And it was not only until the mid-1940s that someone coined this concept, the law of the unconscious statistician. So it's that abstract. Okay, so we'll just move on from here. So from here onwards, there are some useful results that we can use definitely to help us remember this whole concept over here. I'm going to write down 3 useful properties over here so that you can take them down, because you'll be using these 3 properties many times in the exams, all right, whenever you attempt many questions. So the first one is that the expectation of a constant, for example like a, if it does not have a discrete random variable, right? If it does not have a variable, the outcome of a constant will always be a constant, okay? So if the whole thing is just a constant, like for example, the expectation of 2, then of course the outcome you will expect it to be 2, right? So that's the first one. Now the second one is that the expectation of a linear function. So for instance, ax plus b, right? We can see that this over here is a function. Previously just x, right? And then now it becomes ax plus b. So the result from this would be a multiplied by ex plus b. So you can see that the expectation of ex, right, it still remains as ex, and then it is multiplied by the scalar multiple of a, and then plus b is just a vertical shift, right? So you do not expect b to affect or b to it's just everything is just shifted upwards or downwards vertically. Okay, later I'll explain a little bit more on how we actually did write this, but just take this down first. And then last but not least is that if we have 2 different discrete random variables, for example ax and then by, right? Then it'll be aex plus b ey, okay? As simple as that. So let me explain this concept over here. E bracket ax plus b, right? How does this concept over here actually work? So if we were to use this formula earlier on, which I introduced, it'll be taking the summation of all of the ax plus b values multiplied by the associated probability of px equals to x, right? And then from here, what we can do is that we can expand it, right? So you can see you got your rainbow multiplication. So it'll be as good as taking the summation of ax times px equals to x plus b times px equals to x, right? We are just doing the rainbow expansion over here. And then from here, right, since a is a scalar multiple and b over here is a scalar multiple, what we can do is that we can split this into 2 different summations. So you have a summation x times px equals to x plus b times summation of px equals to x over here, right? And then over here you can see that this whole thing, if you recall, this whole definition is just ex, right? So it's just AEX. And then you have your B. And now what is the summation of all of the individual probabilities, right? The summation of all the individual probabilities is 1. Because when you have 10 different outcomes, the probability of all the 10 different outcomes, when you sum them all together, will be 1. Because the outcome has to be either one of them, right? So when you sum everything together, the probability is 1. And therefore, that's how we actually derive AEX plus B, which is what I wrote earlier on. Okay, so you won't be asked to prove this whole thing here, right? You won't be asked to prove that. You are just required to remember these over here and then this. Okay, and once you're ready, you may proceed on to the next section over here, and feel free to pause this video over here to attempt this question. If not, I will begin going through this question right now. Okay, so this should still be relatively straightforward, right? If you understood the formulas that I went through earlier. So for first part, expectation of 3x plus 5 would just be 3EX plus 5, right? The proof has been done in the previous section. So from here, you just need to find the value of EX, right? And what's the value of EX? The value of EX is taking the individual possible values of X multiplied by the associated probability. So it's 1 times 0.6 plus 2 times 0.2 plus 3 times 0.1 plus 4 times 0.1, close the bracket, plus 5, right? And eventually, you get a value of 10.1 as the final answer to this question over here, right? Same thing for the second one. This one, you can view it as AX plus B as well. So AX plus B is the same thing, but now it's just minus X squared plus 3, right? So you can view it as minus 1 times x squared plus 3, whereby the x is x squared, right? If we were to do a direct comparison like this, the x is the x squared. So because we have x squared, we need to first find out what is all the x squared values first, right? And for part I, we actually need to draw another table for this, or we can just extend the original table that we had. Okay, so let me just extend the original table over here, right? And I want to find x squared. So x squared will be 1, 4, 9, 16, right? So even though x is being squared, right, the probability remains the same. Okay, so you will never square the probability. Just take note of that. You're just squaring the x value. So you just imagine it as I got a probability of getting 1. After I get the 1, then I square it. Okay, so I got a probability of getting 2. I've got a probability of 0.2 of getting a value of 2, right? So once I get 2, then I square it to get 4. So that's the idea behind it. The probability will never get squared. Because if you square the probability, then all of them won't sum up to become 1 already, right? Then there's a logical gap over there, right? So over here, we start off with E3 minus x squared, and then it becomes minus E x squared plus 3, right? And then from here, we need to find the expectation of x squared. So it will be 1 times 0.6 plus 4 times 0.2 plus 9 times 0.1 plus 16 times 0.1 plus 3, right? We use all the new values of the x squares over here, as you can see, right? And then we multiply them with their associated probability, and then of course we plus a 3 at the end. So all in all, this will give me a value of minus 0.9 as the final answer to this question over here. Okay, so just note that if it's x squared, we need to extend the table or draw another table, right? If you want to space that. So otherwise, that's it for this concept over here. Let me know if you got any other questions in the comments below. Otherwise, I'll see you in the next video for the next concept on measures of variation, which is again a recap of what we already know so far, but very necessary for the next big concept in this chapter. And I'll see you.